That's all we're going to cover in chapter 14. Level curve, level surfaces, two variable function, and before that we had vector functions, position vector, velocity vector, and acceleration vector. Right? We'll come back to the two more sections in that when we're doing integration. So, introduction to partial derivatives. Partial derivative of a function of a several variable, 2 or 3 usually, are its ordinary derivatives with respect to each variable separately. Very vague, so they came up with a better instruction, which is this one, and we will look at examples and learn how to do mathematics with it, and then after that we understand what it really means. So consider a two variable function f of xy, just like the example we've seen in chapter 14.3 for level curves. We treat y as a constant, that's a key, and look at it only as a function of x with respect to x, and then differentiate it. The result is called a partial derivative of f with respect to x. It's denoted by f subscript x there. So let me introduce other notation. So d dx is differential operator for one variable function, right? And they imitate this one, but they use this round d, right? This round is a partial derivative. So partial with respect to x is the operator. This is the telling you what to do. This is the instruction of this mechanical procedure or mathematical idea. So you can write down your expression here, like that, x plus y. X plus y you recognize as a two variable function, right? Now you're going to treat y as a constant. My favorite constant is pi. So that you know it's constant, but you can't really treat it like 2 or 3. You can't really simplify any further. So I think that's really, psychologically, it helps a lot. So change that y to pi, right? Then how would you differentiate this one with respect to x? X, right? Derivative of pi will be 0, correct? So that's how it's going to happen. Right? Understand this operator? Partial differential operator. Okay, how about partial with respect to y of the same thing? So how is this answer changes this time? If I put pi instead of x and differentiate it, then still 1. That's the partial derivative. Right? So this is a really good notation. If you did not name your function x plus y on the fly, I happen to be having this expression, I want partial derivative, I don't want to name this one f of x, and this is very convenient notation, right? But if you happen to name that function, this function like f of xy, then you will be using this notation, f up there. Like dy dx and df dx, you've seen that notation here, right? Instead, we have a partial notation. And there's a meaning of this partial notation. Engineering the physics, these functions are usually representing the quantity, temperature, heat, exhaustion, whatever the equation. So they use this letter a lot, not just the z, t and omega and all that. So we understand if z is specified like this, the z is a function of xy. Not necessarily we have expression in here. Maybe this is an abstract function. Maybe this is a solution from some partial differential equation. You don't have explicit solution, but you know out there's a solution in abstract form. Then we just use this letter. Okay, z represent this abstract function. I still want, partial derivative with respect to x. So hope this notation makes sense, right? Z represent this quantity that depends on your parameter x and y. Then you can think about partial derivative of z with respect to x, with respect to y, and so on. Yes, sir? It will evaluate to x, y, z, so therefore you have to use a different letter like w. And it's a good question. Sometimes you're all mixed together like this. Can you imagine that something like this? Suppose this is not an equation, right? What is a good name of this thing? This is not a function. What is a good name of this thing? It's a two-word blank. What's that? Blank equation. What is that word blank? Cartesian equation, right? If you have a Cartesian equation, it might look crazy shaped, like maybe it has a hole in there. Who knows? But locally, just around that little point in here, you don't expect that just around that pitch, it looks like a function over xy sometimes. So even though it looks like this, abstractly, we can look at this z as a function of xy. I hope that makes sense. In Calculus 1, this one is called implicitly defined function. So you did the derivative implicit differentiation. So you don't have actual function written down, but if you look at the graph of this one, apparently there is a relationship. If I give an x and y, there is z value associated to it. So there exists this function. We can still think about, okay, that function z, what is the derivative with respect to x and y, right? So you could go any number of variables. But you can't write f of x, y, z and then write z here. That would be weird. You have to choose a different letter for that one. All right? That's a notion of partial derivatives, right? So here's my favorite question again. So if given a function, how many partial derivatives are there? 1, 2, infinitely many. As many as there are variables. I like that answer. If it is 2-variable function, there will be 2 partial derivative. A 3-variable function, like Chris pointed out, there will be 3 partial derivative with a partial x, partial y, and partial z if there's 3 variable, right? I'm glad no one said that there are infinitely many. All right. All right. Write into example and learn the mechanics of this algebraic part, and we're going to think about. So what on earth do this all mean? I'm going to make that a. We're going to do a together. I'm going to make B and C an exercise. So they gave you, so you have to go and review the derivative facts, right? If you don't remember those, a lot of them, and an integral as well. So we have a function, f of xy, x times y plus e to the x times cosine y. 2-variable function. Compute f subscript x, f subscript y. This is very easy for me to typeset. Probably same for those who print this thing, but really when you're writing it, I encourage you to use this notation. This is really good notation and help you. Notation makes sure, kind of form your thinking process. So that's why I'm, encouraging you to do that. But this is easier for us to typeset, so that's why we're using this one. All right, let's do A together. Not an exercise yet. All right, what is fx? Partial derivative x. Treat y as a constant, like pi, like said, is x times pi, e to the x, cosine of pi, right? So what is the derivative of cosine of pi? Yeah, it's not negative sine of pi, right? It's a 0. This whole thing is a constant. Make sure you understand that part. All right, let's do that then. What is the partial derivative? This is what is the answer to the derivative of that part? Y, right? Y is a constant multiple there. Y stays there. Make sense? How about the next one? What happened to e to the x? The only function whose derivative is self, e to the x. How about what happened to cosine y? Is that negative sine y? No, this is just cosine y. This is a constant, right? Right? There's no x in it. It's a constant, like cosine of pi. We just looked at it. Any question about fx? That's a scalar multiple. That's right. The scalar multiple is a cosine of pi. Treat it as if it is a 2 multiplied to e to the x. How would you differentiate this one? Answer is 2 times e to the x, right? Just like that, cosine of pi is just a constant multiplied to function that actually changes. Make sense? All right, let's shout it out what this f sub y is. Partial with respect to y. So let's look at first term. What's the answer? X. Let's do the second one carefully. What is it? E to the x constant, right? So e to the x stays like that as a constant multiple. And what happened to the second factor? Negative sine y. And we better write it like this, right? If you're not too busy, this is a better way to write it. All right? How about part B? Does for f as in a calculate fx at 1 comma pi over 2. Before I make this one as an exercise, I want you to recognize the following. Here's a two-variable function, right? Then this looks like another two-variable function, don't you think? There are two variables, right? They're independent at this point after you've done the differentiation. Here's another two-variable function, right? So if you started with one two-variable function, we created a couple more two-variable functions, right? So I want you to recognize that these are actually two-variable functions as well. So, and their notation is the name of that function is compound notation like this, f subscript x. So this one is simply asking you to plug in x equals 1, y equals pi over 2 to this function that we just created or derived and compute the value. That's what that is. Once you finish with that, go ahead and go part C, see if you can handle this. Compute the derivative with respect to x of this function with respect to y of that function. That too are exercises. First exercise today. Right, and guys, the answer for part B, I hope you agree with that. If you plug in x and y with that given values there, cosine pi over 2 becomes 0. So I only end up with a pi over 2. So this, the word that describes this is the value of the derivative, partial derivative. Does that make sense? This is the value of a partial derivative. Partial derivative is a function, and this is only a value of a partial derivative. So if I continue like this, the value of a partial derivative at where? 1 comma, thank you, 1 comma pi over 2. At that point, 1 comma pi over 2, the value of a partial derivative is pi over 2. But partial derivative, word itself, is referring to a function. All right? Let's go and continue part B. And there was a question. Yes. Very difficult to write all that, but I want you to continue to think about this for for several more days, so that this really helps you to pin down the notion clearly from partial derivative to the values of the partial derivative with respect to something else. This thing is not simple. Just accept that and try to be specific as possible when you think about this, and don't try to oversimplify things. At x comma pi over 2? Where? It's 1 comma pi over 2, not x comma pi over 2. Any point x. Oh yeah, for this problem, for that pi over 2, yes, just for that problem. But yeah, that makes sense then, yes. Because this is going to be 0, and this is going to be always pi over 2, that only picks up y over 2. So he was recognizing, actually, in general, if I put any arbitrary x value and stick it in pi over 2, it seems like it's going to be always pi over 2, right? So, but right, if you just look at this number pi over 2 without out of all context, and that would be still correct, a comma pi over 2. But it was just, but that was a little accident, right? In general, that will be the statement that will stand. Yes. That's the next thing. So right now, we're just going to learn this mechanical part, and then I'm going to show you the picture and then derivatives and the picture and the graph, and this come later. It's a good question. That's definitely something we need to think about. All right, let's do part C. Continue. If you've already done that, just wait for me. Bless you. So I think the tricky part is this differentiating e to the xy squared, right? Using the chain rule. So let me write that down. This part came from partial derivative with respect to x of what function, would you say? That part y squared came from partial derivative of what? The exponent part, right? Xy squared. That's called what rule? Chain rule, right? This is with respect to y. Then you put xy squared in there. Hope you agree. The partial derivative of x times y squared with respect to y will be 2x y to the first, right? So you multiply that. Chain rule. Very important. Any question about the derivative? It's all right? Good. So, loads of problems waiting for you in the homework. Then you keep practicing like this over and over until you kind of, I don't know, you have to keep practicing. So let's think about the meaning of this thing. Notation. Here I'm emphasizing the meaning here, not just fx, but the value of fx evaluated at that a comma b. Now you have numbers like pi over 2. We've seen that before, right? So let's make sense out of what does this number pi over 2 means, right? Derivative, if you think about, it's a rate of change of the value, right? So that's it. That's the one answer here. Rate of change of the value of f of xy. Now we have two directions. If you walk, think about it's the temperature again. F of xy is the temperature. If you walk along the x-axis, especially to the positive x-axis, then negative x-axis is predictable. So positive along the positive x-axis, how is the temperature is changing? What is the instantaneous rate of change of the temperature as you walk along that x-axis direction? At where? Starting from where? A comma B. You're at A comma B. If you walk along that, and what's going to happen? How is temperature changes? And y-axis as well, right? That's the meaning of it. Before you enter graph, that's the meaning of x-axis. Rate of change. It's easier for us to think about this in terms of average rate of change. So suppose that was a comma b. Suppose the temperature there, which is f of xy, was 10. And while I worked along this path 1 unit, then it's going to be a plus 1 comma b, correct? Then suppose that was actually 15. Then you would guess that, oh, here temperature was 10. I walked along straight path like that. Now temperature is 5. So I would guess average rate of change of the temperature is 5 divided by 1. But 1 is like 1 unit. Let's say it's a 1 meter. So 5 Fahrenheit per meter as you walk along that will be one idea, right? But what this partial derivative is really measuring is instantaneous rate of change as you walk along there. So this length is going to be h, not 1 unit. And then you have to divide this one by h and the limit and all. That's instantaneous rate of change. If you walk along this path right here, then might be different. T up there is different. So you expect that, different instantaneous rate of change of temperature as you walk along that direction. Make sense? That's what this one's measuring. So this is the way we're going to understand if it's a 3-variable function. Think about it here. One position in three-dimensional space, you walk along the parallel to x-axis, parallel to y-axis, parallel to z-axis. How is the temperature going to change? That seems like the only way you can handle. But here, 2-dimensional, you can go to the graph and give it more meaning, more entertaining, the picture of this, what's happening there. Yes? What derivative? Right. Do one variable? Two variable, there's only notion of partial derivative with respect to x, partial derivative with respect to y, and there is no other thing so far. Right. Right. It's not the same as one variable derivative. Yeah. So this is a graph of a certain function, and I forgot to copy x-axis, but this is where x-axis is. And I think this is a positive direction. Maybe not. This is where x-axis is. Okay? So this is a point A comma B down there. Comma B comma 0. Make sense? I'm exaggerating. It's supposed to be here, so I know to put it there. So above that, there is this point. Function value, f of AB. That's the z value. Does that make sense? Okay? So, when you're differentiating this one with respect to x, what happened to y? Y never changes, right? Y is fixed. So, if you look at this path here, the blue one, would you agree that all the points in here kind of has the same y coordinates? If you project it on that, it's just like vertical line. So all the y coordinates here is the same. Y coordinate is not changing. Make sense? But x coordinate is changing. So when you're doing the partial derivative with respect to x, you're actually looking at this curve where y is fixed, only x is changing along the x-axis. Then this is one variable calculus. Yes? Excellent point. So as x varies, single variable now, right? Y is not varying, and there's a z dependent variable, and z is changing. That's one variable calculus. In one variable calculus, if there's a graph, what is the meaning of the derivative? The value of a derivative, I'm sorry. What is the meaning of the value of a derivative in one variable calculus? Rate of change? Slope of the tangent line. So, do you see that? There is an obviously plane there, kind of containing this blue curve. And then you can kind of imagine, oh, there's my tangent line right there. Right? That's my tangent line. And what is this slope is representing? No, the derivative is representing the slope. Misspoke. So this is slope of this line over x-axis is the value of the first derivative with respect to x at that point a comma b. Make sense? That's what it means. Very good. Yeah. Alrighty. Then, like Caleb suggested, let's look at the other way around. Right? The same picture. This time, I'm going to include that y-axis so that you can see where the y-axis is. There they are. This is the y-axis there, right? Increasing to that direction. I hope you see the y-coordinates changing and z-coordinates dependently changing. But the x-coordinate here is not changing. They all have the same x-coordinate there, right? So, point is there, and the meaning of f subscript y, fy of AB will be the slope there, right? Maybe m2, so that's a slope. Hope you agree that's a slope right there, right? You know, if you project that over the y-axis, you can kind of clearly see, oh, rise over run with respect to y-axis. You can kind of estimate what that is. But if you have a formula, you do that partial derivative and stick in a and b, and that's a number. That's a slope. Make sense? All right. So I turn this thing around so that y-axis is here, so that you can clearly visualize, oh, that seems like slope less than 1. Would you agree that if you do that slope, it seems like a little less than 1, something like that? That's the meaning. All right. All right. What's different for this problem, you think? 3 variable. Thank you. But principle is the same, right? Principle is the same. So let's get used to computing this one. Now z being another independent variable. So how many partial derivative are we going to look at here? 3 partial derivative with respect to x, with respect to y, and with respect to z. So let's do both of them. And let me just remind you of this neat fact that it's going to speed up your calculation a lot. If you see square root of x, do you know the result of this one? You can change the x to the 1/2, but I kind of memorize this fact. It's really convenient. It's 1 divided by 2 times the square root of x. Of course, again, like I said, the d dx of x to the 1/2, and apply the power rule, you will get the same answer. But square root appears a lot in the standard calculus level, so this is going to help you speed up, save one line or two to get to the answer in a neater form. Yes? Seems like an important point. Y and z are considered constant and differentiated only with respect to x. What is the answer for part A and part B? Here down there is a z, that's what it says. Here down there is z, both of them z. Yeah. And the second problem is with respect to y. Right? Let's compare our answer for part A. So first you differentiate this whole thing as a sine of something, so it's obviously cosine of that same stuff in there, right? And multiply the derivative of inside, which I couldn't do it right away, so I wrote it like this. That's supposed to be the derivative, partial derivative with respect to z of that one there. So I calculate it separately. You see that xy can come outside there like that because it's constant multiple in that situation. So you can go outside, just deal with the z in there, z to the -1. If you differentiate, you get this one. And you replace back and simplify. And then plug in 1, 2, 3, then you get this value. Question? Fair enough? Well, let's see if you can do part B now. Which symbol? Next to the y. This one? This one? Partial? Yeah, this is like this. That's a partial round d. I don't know if it has an official name. Just like you could. Thank you. All right. Any question? What is it? 21st. Oh, I'm done here. I have to plug in those values, right? 0, 1, 1. Yeah. So let me also use introduce notation. Any question at this point before I plug in anything? That's a third power down there. Yes. Any question? It's going so far? Okay. Yeah. So how about this one? This is a derivative of that thing there, x squared plus y squared plus c squared. Answer to this one is this one here, right? But you've probably seen this notation. Put this big vertical line and put down 0, comma, what was that, 1, 1? Yeah. 1, 1. So first, do the derivative, and then you plug in this value, right? Then that's the notation, it's common notation. So you don't plug in 0, 1, 1 here, you plug in 0, 1, 1 here, there, right? So that's negative 1. So 0, 1, 1. Is that square root 2? Raise the third power? Yeah, that's the answer. Okay? Yes, sir?
Later when you took the derivative, where exactly did the negative 2 time come from?
This negative 2? If you differentiate this one with respect to y, that's the only term. This is a constant term, not constant multiple, so that becomes 0. This is a constant term, not a constant multiple, it becomes 0. Derivative of this middle term is 2 times y. This negative came from this negative 1/2 before, so it should be outside like that. It's so that avoid confusion where negative came from here. But it explained 2y. Yes, sir. That's neater, and it's better for multiple choice problem. But if not, you can represent any form. That's fine. Any question? All right. What do you think the next problem is? Oh, just the meaning of that. I didn't even know. So the meaning of this thing. We just differentiate this 3-variable function, right? Let's think about the meaning. The rate of change of the values. We already talked about it. Is you walk along in the space, along x-axis, along y-axis, along z-axis, right? And how the temperature changes. That could be one way to feel this value is the derivative. So here's an example, and does this picture make sense? You're here at this point. If you walk along that position, how temperature changes instantaneously. If you walk along that axis, how temperature changes instantaneously, and so on. Fair enough? Yeah. Next picture is interesting. If you look at this picture, this is a level what? Level surfaces. So here's a 3-variable function, 2x plus, let me just copy that down in the next slide. 2x plus 2y plus z, that represents the temperature in this space. This is where the temperature is fixed to be maybe 8. This is whatever in the middle and things like that. So 3 different levels of temperatures represented. I'm down there in that orange level surface. So I turn around and showing you the situation. You're at this point, and this level surface, it has a certain temperature. If you walk along these 2 directions, you can see you can quickly arrive to the next level of temperature, right? However, if you walk along the z-axis like that, by same distance, you haven't actually reached that next level temperature yet, right? So hope you agree that this seems like have a lowest rate of lower rate of temperature change to the next level, right? Yes. No, this is not a normal vector to the level surface. This is the direction to x parallel to x-axis. This is direction parallel to y-axis. This is direction parallel to z-axis. Always fixed. Not particularly the normal to the level surface is given. So let me go back to the earlier picture. It's like that. Here just always parallel to x, always parallel to y, parallel to z. Maybe you're looking for what could be the direction that maximizes rate of change. That's the normal vector direction. Yeah, but we'll get to that a lot later, not today or tomorrow, next. Yeah. All right, I think I've explained enough about this. We think about what to do next. This is some practice you can do. This abstract thing. All right.